Okay, kinetics. Review part 2. Alright, so we're going to talk about rate equations. And the thing that's important to remember about these is that these must be experimentally determined. Okay, so and we can do that in a number of ways, and we'll see that with examples of problems in class. All right, but the actual rate expression when you ask for that, the equation that they're talking about is rate equal to the rate constant times the concentration of one of the reactants to the x power times the concentration of the other reactant to the y power, and so on, depending on how many reactants. This is for the equation A plus B going to C. All right, remember that the units for that rate, mole per decimeter cube over second, or molarity times second, or moles decimeter negative third to the second negative 1. Right, and those don't change. Please know that or remember that the units on K, these will vary, okay, depending on the overall order of the equation. Okay, so that rate constant K will vary, the units will vary depending on the order of the reaction. Okay, so first order units for that rate constant will be just inverse seconds. For second order, the units for that rate constant would be moles to the negative 1, decimeters cubed, seconds minus 1, and then third order, the units will be moles to the negative second. You swap that around. Did oxidation numbers. Decimeters to the sixth, and seconds to the negative 1. Right. It's also important to remember some graphical relationships for first, second, and third order. And I misspoke. It would be for zero order, first order, and second order. So if we were to plot concentration of A over time for a zero order, it would be a straight line down, the reaction being A going to B. Okay, so here's zero order. First order, also looking at the concentration of A versus time, we would get that kind of a graph. And then for second order concentration of A over time, you would get a much steeper kind of curve. Okay, remember that from where it starts to the halfway point is known as the half-life, and typically you talk about that with first order systems. Nuclear is first order systems, and remember that the T half-life is the time that it takes for half of the reactant to react or disappear. So also looking at another set of graphs, rate versus concentration. Okay, zero order doesn't depend on the concentration, so the rate just remains flat when graphed against the concentration of A. Okay. For a first order, your rate is going to be a linear relationship, rate versus concentration of time, and then for the second order, concentration of time versus your rate, it would look like this. You would, interestingly enough to note, this would be for your concentration of A to the second power would be a straight line. Okay, and I'm hoping that that makes sense. Okay, if it doesn't, please ask. All right, and then the second to last thing to talk about is mechanisms. So reaction mechanisms. And I'm going to go back to yellow. Okay, so remember that the rate of a mechanism is determined by the slow step. And steps in a mechanism are elementary. So you can derive the rate expression right from that equation. Okay, and if the slow step is not first, you have to set up equilibrium equations for earlier steps. And I think this is easier to see in a example. So let's look at two examples. And the first example here will be a slow step as the first step. Okay. So our mechanism would be, say, A plus B reacts to form C plus D. This would be our slow step. Our C plus B reacts to form D, and we'll call that fast. Remember, your overall is just adding these up. A C would cancel. I would get A plus 2B goes to 2D is my overall reaction, but the rate equation, or the rate expression, is taken. We're just going to look at this first step, the slow step. Then the rate is going to be equal to the rate constant times the concentration of A to the first power and B to the first power. Okay, and these ones come from the coefficients here. Okay, so these ones come from here. All right. All right, so now let's look at the second example where we have the slow step second. And let's say we have A plus 2B goes to C, call that a fast step. And we have C plus B goes to D as your slow step. So we're going to write the rate expression for the slow step first. So rate is equal to the rate constant times the concentration of C times the concentration of B. Okay, then for the fast step, we have the rate forward is equal to the rate in reverse. That rate forward is K times A times B to the second power. that's going to be equal to K in the reverse, should be 1, times concentration of C times the concentration of B. We're going to solve this equation for C. So that will be K in the first forward direction, K in the reverse direction, times A over concentration of B. And then we will substitute this into, ooh, I made a mistake. That's not right. Okay. Because if you look at the the equilibrium, it's just that one. That goes here. Sorry, guys. So solving for C, I do get a square there. That's why I was having trouble. So then we can sub this, this expression back into the slow equation. And we will get that the rate is equal to K times K1 over the reverse K times A times B squared times B, which would, these all go into 1K, concentration of A times the concentration of B to the third. Okay, so last topic in the review is going to be activation energy and the Arrhenius equation. Activation energy and the Arrhenius equation. Okay, so this equation is rate constant is equal to A times the E to the negative EA over RT. A is the Arrhenius constant, and it is related to the orientation of the reactants at collision. So related to the reactants orientation at collision. Sometimes also referred to as the frequency factor. Right? We can take the natural log of both sides of this equation and get the natural log of the rate constant times negative EA over R times the inverse of temperature. This, of course, is in Kelvin, plus the natural log of A. Oh, hopefully that looks something familiar in math terms, because that natural log and the negative EA over RT plus the natural log of A. What happens if we plot the natural log of K over 1 inverse T in Kelvin? Okay. I would get a line, and these would be kind of my data points, and fit a line to it, right? That slope is going to be equal to negative EA over R. Remember that you're going to have to use R in energy units, which is that 8.31 joules per mole Kelvin, I think. Right? So graphically and through experiment, you can determine the activation energy of a reaction. And if you were to extend this line, you would get the natural log of A as your y-intercept. Okay, and just a quick rule of thumb. We'll write this in purple. Rule of thumb. Okay, if you increase temperature by 10 degrees, you double the initial reaction rate. And again, that's just a rule of thumb. I think that purple's kind of hard to see, but the most important thing is knowing Arrhenius' equation and how to experimentally determine the activation energy. And that will conclude the review.